The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. My name's Helen Miller from Ohio EPA, and we will be starting the webinar in approximately 1 minute because people are still logging on. So in 1 minute, we will start. Good morning, everyone, and welcome to our webinar, Ohio EPA's Troubleshooting Noncompliance for Smaller Mechanical Wastewater Treatment Plants. This webinar is part of our In Your Community webinar series, which focuses on environmental issues at the local level, covering a wide range of topics from how Ohio EPA regulates pollution sources to ways on improving the environment in your local area. My name's Helen Miller with the Division of Environmental and Financial Assistance, and I will be moderating today's webinar. Our speakers today are John Van Dommelen, Nick Hammer, and Andy Gall from the Ohio EPA Compliance Assistant Unit. Before we get started, I'd like to go over a few items to help you participate and engage with the presenters today. On this slide, you see a screenshot of your attendee interface. You should see something that looks like this on your computer desktop on the right-hand side of your screen. For this webinar, you are listening in using your computer audio. If you're having sound issues or if the slides stop advancing, please try refreshing your browser. If that doesn't work, try logging off and logging back on. Please feel free to submit questions to the presenters by clicking on the question mark icon and typing them into the questions pane on the attendee interface. You may send questions in at any time during the presentation, and we'll do our best to answer questions as they come in. We'll also address some of the commonly asked questions during the Q&A portion at the end of the presentation. If we're not able to respond to your question during the webinar, we will reach out to you via email after the webinar. To view and download the handouts, please click on the Documents icon on your attendee interface. A flowchart and manual that accompany this presentation are available. This webinar is being recorded, and you will receive an email after the webinar with the link to the recording and the link to the session survey. The survey will also pop up once this webinar ends. We value your feedback and would greatly appreciate it if you let us know how we're doing. Let us know if there's anything we can do to further assist you. Please note, you will be sent your certificate of attendance in a separate email from an Ohio EPA staff member several days after the webinar, not from the GoToWebinar platform. This webinar is approved for 3 contact hours toward wastewater operator certification. To receive credit, you must attend the entire webinar, and it must be the primary window open on your screen for more than 90% of the time. You must also participate in all live polling questions. There are 12 polling questions throughout the 3-hour webinar. To make sure you can see all the polls, please maximize your screen. If you miss a poll question, please send in a question in the Q&A panel. That way in the report, we can see you are actively participating in the webinar. If you are seeking wastewater operator certification contact hours, please provide your core person ID in the post-webinar survey so we can submit on your behalf to the Certified Operator Program. This webinar is also approved for 3 hours of registered environmental health specialist and environmental health specialist in training credit. To receive credit for attending, please provide your REHS or EHSIT number in the post-webinar survey so Ohio EPA can submit on your behalf to the Ohio Department of Health. If you have questions on CEUs, please refer to the CEU fact sheet in the Documents section of the attendee interface. Today, we will also take a 5-minute restroom break approximately halfway through the webinar. So we will extend the length of the webinar by 5 minutes, ending at 12:05 p.m. With that, I'm going to turn over the mic to our first presenter, John Van Dommelen.
Hi, My name is John Van Domelen, and I have been in the CAU for about 23 years, so I have quite a bit of experience. So here, oh, a second. There we go. There I am on the left, rigging a sand filter. In the middle is Nick Hammer, who is in Southeast District office, and he's doing some chemistry at the side of the wastewater treatment plant. And on the right-hand side is Andy Gall in a sewer. Okay, so we actually do a little bit of everything. Okay. So we're going to take a quick poll right now to get started. And here is the poll question. First question is, are you an operator, an engineer, or other? And the 5 that you can choose from are certified operator, an uncertified operator, professional engineer, the owner operator of a small system, or other. Please select one.
Okay, I have launched the poll, so as it comes up on your screen, please make your selection.
I take it they fill in the dots?
Yes.
Okay.
And then hit submit. Yep, and then they have a submit button on their end as well.
Ah, okay.
It's looking like a lot of people have voted. If you have not made your final selection, please do so. And again, a reminder, if anybody logged on a little bit late, if you are looking for the wastewater ops cert credit, you do need to answer all 12 polls this morning. Okay, I'm going to close out the poll here.
Okay.
And share the results. There you go, John.
Okay. Well, it looks like 39% are certified operators. There are no uncertified operators. There's 11 professional engineers. There are 3% or 11%. 3% operator owners of small systems and 47% of others. That's interesting. Okay. Wonder what the others are. Okay, so now we're going to go into the activated sludge process control and troubleshooting chart. Okay, I've been doing this, like I said, for 23 years, and I have pretty good control over what's wrong with treatment systems. So, to begin with, way back in about 2000, well, the middle 270 or 1970 something, the Clean Water Act was enacted, and Section 104G1 was the section that provided for training for operators. Now in Ohio, the federal grant was used for equipment, supplies, travel, and training for us, okay? But some of the other states usually used it for their FTEs, and so they didn't have a whole lot of training equipment. But in Ohio, our positions were funded through normal revenues. But most importantly, and I say this very sincerely, the CAU had the support of management, and that is just so important for the CAU, to be honest. So what we do is we provide on-site technical assistance to communities. And I really mean that. We do on-site. We go to the treatment systems. Typically, we go to smaller systems. You know, the smallest ones are about 1,500 gallons per day. But we also go to large systems too. And if they have treatment issues, we can go and solve those problems as well. But what we do is we help operators overcome non-compliance with their NPDES permits. And you can call us directly. You can call your inspector, and then they can send an email to us, and then we can call you. But this is really how it works, okay? We will get in touch with you one way or another. So when we go to technical assistance for certain communities, we troubleshoot all aspects of wastewater treatment. It doesn't depend just on one thing. We can do all sorts of things. And process optimization, or process control, I like to say, we use cheap because nobody has money, okay? Easy, because if it's difficult, who's going to do it, okay? And if it's not effective, why bother? So our process optimization using cheap, easy, and effective process control tools is the key. In the Compliance Assistance Unit, what we do is we view wastewater treatment as a biological process, because it is. The bacteria do all of the work in a wastewater treatment system. But what we do, we measure the physical characteristics. We sometimes use visual cues, and we look at the chemical trails that the bacteria leave behind as they convert the pollutants in wastewater into carbon dioxide, nitrate, and more bacteria. Okay? Another poll. Wow. Okay. So let's take this other poll. This poll is, DEPA's CAU provides assistance in how many of Ohio's 88 counties? All 88? 3? Not sure. Please select one.
Okay, and I have launched the poll, and please enlarge your screen, go to full screen if you're having issues seeing the polls. That can help you. And again, please take the polls through the polling tool by clicking on the different, options A, B, C, and then there is a submit button as well at the bottom of your poll. Okay, please wrap up your selection. It looks like a lot of people have made their selection, but I will be closing the poll shortly. Okay, I'm closing the poll and sharing the results. There you go, John.
Okay, well, looks like people know what we do. 93% say all 88 counties. 1% said 3, and 6% weren't quite sure. So anyway, that's that. And there we go. This is our activated sludge process control and troubleshooting manual and flow chart. On the left-hand side is the flow chart, and on the right-hand side is the training manual, which is about 56 pages long, I believe. These are available in the handouts, but we did this back in about 2014, 2015, and it's a really good system, because in the flow chart We have all the things that will impact uh, ammonia control, and we also have, those are the things in the gray boxes, and in the yellow boxes we have things in the middle for you grew the wrong kind of bacteria, or on the right hand side you have clarifier issues. But the good thing about this is each of those boxes has a number at the bottom, and each of those numbers refer to a page in the training manual. Okay, so there are about, I don't know, well, there's about 29 or 30 pages connected to the boxes, but then at the back of the activated training manual, there is a thing that says, how do I ... and in order from box 1 down to page 29 or 30, it will tell you how to do the chemistry. Okay, so that's what the training manual and flowchart in the handouts are for. Okay, so the world of noncompliance, causes and fixes. Okay, now there are about 3 different things that will cause noncompliance. Now, operational issues, that's the big one. But process control, if you're doing process control, you can see that it's starting to go towards non-compliance, and you can bring it back. Okay, but if you're not doing process control and you're just sending your chemistry out to a contract lab, you won't get the results back for maybe 5 or 10 days, and that's too late. So if you can do some process control at your plant, that will work so much better. And maintenance as well. All the treatment systems have to have good maintenance. Okay, so the second thing that can impact your NPDES permit are design issues. Some of the small treatment systems don't get the best engineers sometimes, and sometimes the plant is designed to work one way. Okay, and sometimes you might have to do some increased process control. Instead of doing it maybe twice a week or something, you might have to do it 3 times a week, 4 times a week, or if you are in non-compliance, you might have to do it every day for a while. So, or if there are workarounds for poor designs, we can help you work or figure those out as well. And there are administrative issues. This is where the funding comes in. Do they have enough staff? Do they have enough to pay the staff? Or the operations, maintenance, and replacement costs, if they're, if the administration is kind of skimming a little bit of that off for something else, that is really what the sewer bills are used for, to save a little money, so when something breaks down, you have the money to pay for the improvements. Okay, so that's that. So now we're going to start looking at some of my welcome to my world. Okay, this is a small system training plant, or small system plant. Doesn't look very sufficient, but it actually worked very, very well. It doesn't have to look nice to work well. Okay, and this one certainly did work pretty doggone well. Okay. Here is another one. I know that there's a treatment plant here someplace, because I can see the housing for the blower right there on the lower right-hand side, and I can see a little bit of concrete and a little bit of some grading there too. But weed whacker would probably do this plant a very good job, because I don't think they were doing very much process control at this plant with the weeds growing like that. Okay. This is a treatment system. There's a lot going on in this picture. As you can see out there on the other side of the fence, there is a concrete slab, and that was a vault for the that goes to the wastewater treatment plant way in the background there. But the pipes broke, and it spilled all over the ground and killed all the grass, and that's all piled up in the back of the yard there. But there's a couple other things too to look for. Now, if you look at the control box, that's the box with the red light on top and the rusted bell on the side, you can see that the top is locked or shut, but the bottom is not, and there are wires coming out. That's not a very good system. Probably should have gone through that conduit right there, but it didn't. And if you look at the lower right-hand side, there's a rusted pipe sticking up with a brand new chain wrapped around it. And that is holding the pump in the bottom of the wet well a little bit up off the ground so that it pumps sufficiently. So anyway, that was a pretty bad system. And to be honest with you, the aeration tanks had, well, one of the aeration tanks had about 3 of about 20 down, or 3 of the 20 drop pipes that provided air to the system, only 3 were working. So that was a good one. But we went in, we had the local community come in, and we manufactured some pipes, some drop pipes and such. In about a week, we had it all working except for the disinfection, because that was a little late coming in. So. Okay, so this is another treatment system, a little bit larger one, and they were wondering how come they didn't have enough DO in their system. Well, looks kind of obvious, because that rotor right there was missing about half of their paddles that creates the DO in the water. Okay, so yeah, that's welcome to my world. And here is another system, a little bit larger system too, and this is a clarifier, and the flow comes into the center ring of this clarifier. And as you can see, they have a lot of dried sludge on the right-hand side, and they have some plants growing there too. And those plants didn't grow overnight. Those plants have been there for quite some time. You would sort of think that they would probably pull those plants up and get a vac truck and pull the dried sludge off, but no, they didn't. So anyway, welcome to my world. This is another system. We were doing a House Bill 110 for this treatment system, and we asked them. We did the presentation in the morning, and then we asked them to line up a couple of treatment systems, and this is the first one we went to. And you could hear the blower running, but we came in through the backside, and this is the clarifier, and the pipes were totally rusted away, but the air was still coming into the clarifier. It wasn't moving any sludge, and it was aerating the clarifier, okay? Not a very good system. Oh, and this is the chlorine contact tank too. So this one didn't seem like it had chlorine in it for quite some time, obviously. Okay. Okay. Well, this one shows a block in a flow channel. Okay. This is where the influent flow comes in, and the operators are some of the most creative people in the world because they can tell when one tank is full or one tank gets most of the flow and the other tank gets very little flow, and then they will do something to try to balance it out. Well, they put a block in, and that's pretty common. But the blocks are, they're not really all that useful to get the flows right. And they have a spare block right there on the side. But anyway, they're trying. Welcome to my world. Ooh, and this one, this is this is Nicardiofoam, okay? And this Nicardiofoam is about, I don't know, 2 feet thick, okay? But they had a subsurface takeoff in the back of that tank. And what it did was, if you have a subsurface takeoff, it takes flow from the bottom, but it doesn't clear anything that floats in the top, okay? And every morning when the operator would get in there, this tank would overflow when the morning flush came in. And you can see down the very bottom right-hand corner, you can see on the floor down there's Nicardiofoam. And the operator would come in, he'd hose it back to the drain, which would go into the influent pump station and would pump back up again. So, but we did fix this. What they had here was 3 tanks in parallel. And what we did was we took 1 tank out of service. We put 1 tank going down and the other tank coming back. So we made them in series rather than parallel. And we had the vac truck come in and suck all of the Nicardiofoam off twice because it came right back. But then we adjusted the pH a little bit and with some bicarb, and it didn't. The Nicardia more or less disappeared, and you could see the water underneath it, and it didn't do it anymore. That was a very big success. Okay, here is another clarifier that's getting ready to lose its lunch. Okay, so that's that. Okay, so here is what is this? Is this a sludge drying bed or is this a sand filter? Well, it is a sand filter, okay? And they had a lot of sludge leaving the clarifier and going to the sand filter. Now, if you look at the very top part, the top right-hand side, you can see that the sand bed next to it is pretty much looks like this one. If you look at the left-hand side up at the top, you can see a reflection of the trees, which means that that's water and it is flooding the system. So probably at the sand interface, it probably looks like this one too. So this is a plant that had a series of solids loss. Okay. The next one is, well, again, this is return sludge, and the operators kind of fixed it. They put these bricks in and guided it to the where the return sludge would go into the aeration tanks. And what they did was they built some new clarifiers, but they used the same sludge pumps, and the clarifiers were a little bit too far away, and it came up through the ground, and so they built this, and it worked pretty well for a while. So we'll see. And this one is this was a good one. This was one that, as you can see, the pipe is a 4-inch pipe, and the manhole core was an 8-inch pipe. okay, for an 8-inch pipe, okay. So what we did was we were sent there because in the spring, when when there's a lot of rain and snow melt and everything else, but all of the mainline manholes were flooded, okay? And so we really couldn't do very much. But then later on in the summer, towards the end of August, we were driving to another treatment system, and we drove past this community, and we thought, wow, it's been pretty dry. So we went and we popped a manhole, and the manhole was about 20 feet deep, so it was pretty deep, and you couldn't really see down into the bottom of it. So we took our digital camera, put the flash on it, took a picture, and this is what we found. Okay, we found that there was no gasket around the pipe. Okay, and the pipe was drilled for an 8-inch pipe and 4-inch pipe. This is a small diameter gravity system. And you can see the bedding back there on the upper, just to the left of the pipe, the gravel, okay, and that's what they put, that's the bedding that they put into the, keep the pipe stable. And this was up in Northwest District, and you know, the soils are pretty tight up there, but the flow, once it gets down to where the gravel is, it flows pretty well. And so we had a lot of I&I coming in on the outside of the pipe, and you had sewage coming in through the inside of the pipe, okay? That was, and we took this photograph and we took it to the village administrator, and he was kind of shocked. And, but he actually ended up getting a, sealing all these manholes in the main line, because it was really, really bad, okay? So these are our tools that we use all the time for small plants, for big plants, for all plants, okay? Now in the upper left-hand corner is my DR900. If you buy the chemicals or the chemical kits, it will give you a number for each of the tests that it can do, and it can do about 100 different tests. It can do the organics, it can do ammonia, nitrate, orthophosphate, CODs, sulfides. It can do about all sorts of metals and such. But anyway, it works really, really well if you buy the chemicals, or if you buy the chemical kits, okay? But below that, the API ammonium nitrate is the same chemistry that the DR900 uses, but you use it a little bit differently. And you, the ammonia test takes about 18 minutes for the DR900, but for the ammonia kit, it takes about 8 minutes, and then you match the color of the chemicals make different colors, and you match the color to a card, okay? And they have about, I don't know, 6 or 8 stripes of different colors. And so anyway, I've done it side by side with the DR900 and the API kit. And if the API kit is less than about 1.5 milligrams per liter of ammonia, the DR900 will support that. But if it's greater than about 1.5 milligrams per liter, all bets are off. So I call the ammonia or the API test a pass-fail test. It's either less than 1.5 or greater than 1.5. If it's greater than 1.5, you probably have, it's probably way greater than 1.5. But you get a number if you buy the Hach DR900. But that's about $1,500. That's a little expensive. Okay, next to the DR900 is the alkalinity test kit. Now this is really important, especially in places where they have water conservation, because if you have water conservation, your ammonia is going to go up, but your alkalinity is going to go down because the alkalinity is in the carry water, okay? The water that flushes toilets or goes down the drain or in washing machines, whatever. But in the nitrifying bacteria, the bacteria that converts the ammonia to nitrate uses inorganic carbon. And the pHs that are in a wastewater treatment plant, that is bicarbonate, okay? Sodium bicarbonate. So this will measure sodium bicarbonate, and we'll get into that a little bit later, but it will, and the bicarbonate ion will go down to about a little less than 5 pH, but nothing's going to work down there. So you have to have at least about 100 milligrams per liter of alkalinity when your ammonia is less than 1, okay? And for alkalinity, if you take an ammonia test and it's high, you multiply the ammonia test by 7, and that will tell you, and then you add 100 to that, and that will tell you how much alkalinity you need to oxidize all the ammonia down to 1. Okay. Below that is a dissolved oxygen probe. You can use that if you are doing parallel treatment systems. They should be the same in the first tank and then a little bit higher in the second tank. The first tank, if it's pumping raw wastewater into that first tank, it's going to be pretty low because the bacteria will use all of the DO that you supply. Okay, so it'll be pretty low. But if you have vaults or like package plant vaults, and the first tank might be pretty low, but the second tank might be higher. And if you have a third tank, it should probably be even higher, the dissolved oxygen. This will tell you what the DO is. And you should have around about 2.0 to 3 at least in the last tank going to the clarifier. Okay, now if you go over to the right-hand side, that is the wastewater centrifuge. This is a great tool. It's pretty expensive. Again, it's like $1,500 or so, but it will do so much. I can put, there's 6 vials in there, and I can put 2 of the aeration tank in there. I can put 2 of the core samples in there. I can put 2 of the return sludge samples in there, and I can spin them all down, and I can see how much is in each one. And below that are the sedilometers. If you can, one on the right-hand side, it settles pretty well, down to around 650 in about 5 minutes. But the one on the left didn't settle very well at all, okay? It's about 950 in 5 minutes, and it probably is filamentous, okay? If it doesn't settle very well, you can pretty much guess it is filament that you've grown a filamentous sludge, okay? And here are the tests, doing it in person, okay? There's the sedilometers up above again, but below that, there I am years ago, doing an alkalinity test kit, okay, and looking at it. There I am again with the DO probe, and I am at the end of the tank, seeing how much DO is in that position. Next to that, above, are the centrifuge tubes. The one on the left is that's what it looks like when you pour the aeration tank or the RAS or the core sampler into it. And on the right-hand side is what it looks like after it spins. It spins at about 5,000 RPMs, and it it takes 15 minutes. And you can tell how much mass is in the aeration tank, in the core sample, and in the RAS just by using this, okay? Below that is a alkalinity or a ammonia test kit. This is a single parameter test kit. It will just do ammonia. And for this particular experiment, it is 0.20, which is pretty low, which is good. And over on the right-hand side is Keith, who's now retired, but he and I were did this for years together. But he has about a 5.5 foot core sample from the clarifier, and when you have that much core sample in a clarifier, it will probably go to septic before it gets to the bottom of the where the return pump is. Okay. So we're going to take a quick poll here, and then I'm going to turn it over to Nick, and he's going to talk about conversion. Okay. So the number 3 polling question is, how big is your wastewater treatment plant? Is it small, less than 100,000 gallons per day design? Is it medium, maybe 100,000 to 1 million gallons a day design? Is it large, 1 to 5 million gallons per day design? Or is it very large, greater than 5 million gallon per day design? Or you don't operate a wastewater treatment plant? Please select one answer.
Okay, I have launched the poll, and as the reminder, if you're having difficulties seeing the polls, please extend your screen to full size. On the GoToWebinar interface, there's an icon that has 4 arrows in each. There's an arrow in each corner that will make your screen size go to full screen. And also as a reminder, there are several handouts you may want to download. There's a copy of the PowerPoint slides as a PDF file in the handouts. There's also a manual that John mentioned earlier and a flow chart that he mentioned earlier, and then a fact sheet on our CEUs. And it looks like most folks have voted, so wrap up your selection if you have not. And I am closing the poll and sharing the results. There you go, John.
Okay, thank you. Well, about 9% are pretty small, less than 100,000 gallons per day design. 17% are medium, between 100,000 gallons and 1 million gallons. Okay. There are 10% between 1 million and 5 million gallons per day. And there are very large, greater than 5 million gallons a day design, 11%. And there are 53% that don't operate a wastewater treatment plant. Okay, that's okay. Okay, so this is the solution to all of those problems that occur in wastewater treatment systems. Okay, Nick, would you care to take over?
Sure, yep. I'm
Okay.
ready to go here.
Okay, go ahead and.
Okay, so first things first, as Helen mentioned, some of the handouts to download. If you happen to have the activated sludge process control and troubleshooting chart printed off, it would be helpful to have that kind of alongside with you here. You can kind of follow as we work our way down the chart, troubleshooting the issues. So we're going to start at a very basic level, just a real quick concept for everyone of what's happening at a wastewater treatment plant. So in the aeration basin, the pollutants, so your CBOD and your ammonia, they're converted to more bacteria. And then in the clarifier, the bacteria are separated from the clear water. So the bacteria can be returned back to the aeration tank so they can go back to work, and then clear water can be discharged. And what I'm going to talk about today on my portion of the presentation is actually going to be the conversion of the ammonia to nitrate, or possibly the lack of conversion of ammonia to nitrate. So here's that troubleshooting chart that we referenced that you've seen a couple times so far in the presentation. And what you do with the chart, you start at the very top on box number 1, and the left side of the chart, the blue boxes that are circled right now, those are the conversion portion, so they're converting the ammonia to nitrate. And the right side of the chart is what Andy's going to be talking about here in a little bit, and those are all separation issues. So it may be clarifier issues, or it may be type of bacteria or filament that is growing in the plant. So back to kind of to square one when we start with the first box, which is a question. You know, most of the boxes ask a question, and then you respond to that question based on what the results are. If the answer is no, you follow the red arrow over to the left, and if the answer is yes, you follow the green arrow over to the right, and you work your way on down the chart. Keep trying to identify what limiting condition or what is occurring at the plant that's causing non-compliance. So each box will either request more data or it will help identify the issue. And then you continue working your way through the chart until you reach box number 24, which is you're in compliance. So we're going to jump into another poll here right away. So it's poll question number 4, which the question is, what are 2 basic things that an operator must achieve to maintain compliance? A, dissolved oxygen and CBOD. B, TSS and chlorine residual. C, conversion and separation. D, pH and ammonia. And E, nitrate and orthophosphate.
Okay, I have launched the poll, so go ahead and click on your button for your selection and then click on submit after that. Okay, it looks like most people have voted. If you have not, go ahead and please make your final selection. Okay, and I will be closing the poll shortly. And sharing the results. There you go.
Okay, so it looks like about half of the group selected conversion and separation. That's great. That's what we're talking about today. That's the CAU method. With the chart is based on. About a quarter selected DO and CBOD, and pH and ammonia 17, and then so everything is important for compliance on here depending on your permit requirements, but we're talking about conversion and separation today. So there's really no wrong answer. So, okay, so we're going to jump right into the chart here. So we're going to start. Once again, everything that I'm going to be talking about today on my portion is going to be that left side of the chart, those blue boxes, if you have the chart sitting in front of you. So when we're talking about conversion, we're talking about converting all the pollutants, so the CBOD and the ammonia, and converting them into more bacteria. So we start with our chart at the very top, box number 1, which states, is the clarifier effluent ammonia less than 1 milligram per liter? The CAU, we run process control tests on ammonia because we can easily have an ammonia concentration within 20 minutes or so in the field. The CBOD test, it's a 5-day test, definitely not a field parameter. We want to know what the answer is when we're out there in the field troubleshooting on that day. Additionally, nitrifying bacteria are more sensitive to poor conditions in the aeration tank, and most of the time, if there's little to no ammonia, the CBOD will also be very low. It's not very common to have CBOD violations and not also have ammonia issues or violations. So for mechanical plants, what we're kind of talking about today and what the chart is mainly geared toward, we consider a result of less than 1 milligram per liter of ammonia complete conversion. And anything over 1 is a result of some limiting condition that's preventing complete conversion. This is the basis for the entire left side of the chart, the part that I'm talking about today. We'll work our way down the chart until we identify the limiting condition that's preventing complete conversion of ammonia to nitrate. So first question is, how do we measure ammonia? Well, as John kind of alluded to in one of the previous slides, the CAU, we use the multi-parameter meter, which is here on the left side of the screen. The ammonia fish test kit, that API kit John referenced, is here on the right side of the screen. They're both, they use the same chemistry. The DR900, or in this picture, the DR890, it is fairly expensive. So if you can't afford that, the little fish test kit, ammonia test kit, is a pretty good option. And what you do is you match the color to this little tab that comes in the test kit. So you're just, taking what the reaction happens in the tube, matching it up. And as John mentioned, really anything 1 or below, we feel pretty confident that you've got low ammonia. Anything above 1, it's really hard to say. It could be 10, it could be 5, it could be 20, but it's fairly accurate when the color is in this very light yellow to very light green. It's going to be fairly representative. And as John mentioned, it's more of kind of like a pass-fail test, the fish test kit. The actual meter will give you a number and a result. This is just, depending on how you look at it and match it up, you can't really go by that. And one thing I want to make note of here, both of these are not to be used for final effluent sample reporting to Ohio EPA. They're great for process control, what we're doing, but they are not approved to report your final ammonia to the agency for your NPDES permit. As John also mentioned, the multi-parameter meter, within 20 minutes, you have a result, ammonia result on whatever you're testing. And in about 5 minutes, the ammonia fish test kit takes to react, and then you you match it up to that card. Okay, so what we're going to do here, we're going to assume that the clarifier effluent ammonia is greater than 1. So we would follow the line, and that would take us to box 2, which states, is the aeration effluent ammonia less than 1? So, I think probably a good amount of people on the call today know that the clarifier is not there to remove ammonia. So what we do is we sample the aeration tank and we sample the clarifier to get the ammonia concentrations or the ammonia results for both of these environments. If the water entering the clarifier is greater than 1, then we know the clarifier effluent will also be greater than 1. So in this top picture here, if the ammonia is greater than 1 in the aeration basin and it's greater than 1 in the clarifier, we know the problem is incomplete conversion in the aeration basin. On the flip side, this lower portion of the slide, if the ammonia leaving the aeration basin is less than 1, so we're getting good conversion, we're reducing that ammonia, but the clarifier effluent is greater than 1, then we know the problem's not conversion because we converted the ammonia to nitrate in the aeration basin, but the problem is actually located in the clarifier. And that leads us to what could be causing solids to break down in the clarifier. Why are we getting a release of ammonia in the clarifier? Well, in this picture, you can see here's a scum baffle. You can see all the solids in the scum baffle, and this is part of the clarifier. You can't see it all. What happens over time as the solids, the bacteria accumulate in that scum baffle, they'll build up over time, and if they aren't removed, those bacteria will begin to start to die. And when bacteria die, they can release ammonia, and that ammonia release back in the water column can cause for elevated ammonia in your clarifier effluent. Here's another picture kind of showing the same thing, just a little bit larger plant, showing a circular clarifier and a flocculation chamber. You can see the large amount of solids that are sitting in the flocculation chamber, and you can tell they've been there for a while just based on the vegetation that's growing there. So that's another possible source where ammonia could be released into the clarifier. Another source is from the clarifier surface. So here in this picture, the entire clarifier is covered with a thick layer of solids, with the exception of the outlet weir, and here's the outlet baffle. And what happens in a situation like this, the solids sit on the surface for a long period of time, and they can also release, just like in that scum baffle, they can also release ammonia or a source of ammonia into the water column of the clarifier. Here's another picture of just a larger clarifier, circular clarifier with a large amount of solids on the surface, just another potential source where ammonia could be released in the clarifier. And then another source could be in the actual clarifier sludge blanket. So the picture on the left here shows John holding a core sample. And if we zoomed in on this picture, you can see that the core sample, the water depth in the clarifier is about 10 foot. And it shows that it's about 8.5 foot of solids in that core sample with, about a foot and a half of clear water on top. So when the solids are occupying roughly, 85% of the clarifier, that just means they're staying in there too long, and they'll start to begin to break down, go septic in the bottom of that clarifier. Clarifier is not an aerobic environment, so they'll start to lyse and release some of their ammonia back into the water column. So a very thick sludge blanket can be a source of ammonia release in a clarifier. So regarding box 3, so at this point what we've determined, if you have your flow chart, is that we've answered no to box 2, which stated that aeration effluent ammonia was less than 1. So we've now jumped over to box number 3, which asks the question, is the aeration effluent water temperature less than 10 degrees Celsius? Temperature is very important, mainly in the winter time. When the temperature in the aeration tank drops to 10 degrees Celsius or lower, the bacteria start to slow down. They become less active, especially nitrifying bacteria that we're looking at for ammonia removal. The colder temperature also results in a slower growth rate of the bacteria, and in turn you can have slower conversion of ammonia to nitrate. So in this picture, here's a DO probe. The DO is actually up here, but what the red circle is showing is the water temperature in the aeration basin, which is 7.9 degrees Celsius. The bacteria will most likely still nitrify at this temperature, but at a much slower rate. So anytime you have a water temperature in the aeration basin of less than 10 degrees Celsius, there's a potential for elevated ammonia there, because the bacteria just aren't going to be oxidizing that ammonia quite as quick. So let's say, for an example, we've determined that the water temperature in the aeration basin is less than 10 degrees Celsius. Well, the flow chart then takes us to box number 6. What do we do? Well, on a small system, like in the diagram here on the screen, you might be able to take a treatment tank, so one of the aeration tanks, or possibly even an entire treatment train out of service. So when you have high organic loading, the bacteria metabolizing the pollutants will generate heat and tend to keep the aeration tank and mixed liquor, warmer than the outside environment. However, if you have low organic loading, then you have less bacteria metabolizing and less heat is generated in the aeration basin. So, based on that example, so say we have low organic loading in the winter, one option to help reduce heat loss is to reduce the aeration capacity. If the piping is present and you could, bypass, the first aeration tank, send the raw right into aeration tank 2, you take that first tank out of service. Well, the reason for this is we want to match the amount of online aeration to the organic load coming to the plant, and that will help reduce the amount of heat loss to the atmosphere. So one thing to keep in mind is you wouldn't want to do this if you're experiencing high levels of I&I, or you're up against your design, you're even dry weather flows, you're at your design capacity. But this is one option to help reduce heat loss and to keep that temperature, hopefully, 10 or around 10 degrees Celsius. Another way to help minimize heat loss in the aeration tank is to use a timer on your aeration blowers. We are big advocates for timers on small systems. If you think about a small system, most of them are not getting flow 24/7. Something like a school, church, small business, gas station, most of their flow is usually being received during the day and very little overnight, maybe even none overnight. So with little or no flow coming in at night, in turn, that means there's little to no food for the bacteria that's entering the plant. Therefore, your DO demand would be very low in the winter, or at night when there's very little food coming in for the bacteria. In addition, you think about it, most small, package plants, the aeration tanks are buried in the ground, and that also helps provide some level of insulation for the mixed liquor in your aeration basin. So if you're able to run the blowers on and off at times, you are able to conserve some heat in the aeration tank. One thing to keep in mind, though, with the timers is you never want to go very long extended periods of time with the blower off, because not only is the blower aerating and adding dissolved oxygen in the aeration basin or aeration tank, it's also functioning to return solids from the clarifier in most plants, and it returns the return sludge back to the aeration. So if you have extended off periods, you run the risk of denitrifying the solids in the clarifier, which would then cause solids to surface on the clarifier, and you could lose solids. And Andy's going to go into a little more detail on that here when he gets to his portion of the presentation. Another option to try to reduce heat loss in the winter, especially for small systems, this doesn't really apply if you have a large plant, would be covering the aeration basins, equalization tanks, and or the clarifiers. The plant in this picture here used styrofoam with all those concrete blocks to try to help insulate the small plant in the winter to minimize some heat loss. Another good option that I see on a lot of plants that I go to is kind of like heavy rubber mats. Some have used like stall mats from like a dairy farm. They're really heavy, so they're great. They don't blow away. And they usually just place them on top of like the grating on the tanks to help conserve some heat in the winter. You can see, a lot of this is kind of typical grading that you'll see on a lot of package plants, and you can see how well the styrofoam, this operator cut the styrofoam to fit into those grates. One other benefit, a kind of a side benefit of covering is a lot of operators or a lot of plants will go ahead and cover their tanks in the fall or early fall, late summer. That way, when the leaves start falling, if you have a lot of leaves around your plant, a lot of trees, it prevents a lot of that from falling into the system. I've seen several small clarifier returns get plugged up with, leave and other organic matter that are falling in. So that's kind of another little benefit of covering. So it looks like we're up to another poll question. So this is poll question number 5. How do you measure ammonia concentration in your wastewater treatment plant? A, I don't. B, ammonia probe. C, ammonia test kit. D, I send samples to a contract lab. Or E, I use an aquarium or the fish test kit. Please select one answer.
Okay, I have launched the poll, so please make your selection. And it looks like a lot of people have voted. If you have not, go ahead and please make your selection before I close the poll. Okay, I'm closing the poll and sharing the results. There you go.
Thanks, Helen. So looks like about 43% do not measure ammonia concentration in their wastewater plant. And then, 13 to 21% use a probe test kit or send it to a contract lab, and then 5% using the fish test kit. So, we encourage a lot of plants to do process control, checking the ammonia, and, something as cheap and simple as an aquarium test kit, can get that done. Okay, so back to our flow chart here. So where we're at now, box 5 would be, if you have your flow chart handy, we've answered yes to box 3. So that would take us that we have greater, we know we have enough temperature, so that's not our limiting condition. And then box 5 has us looking at checking to see if we have enough alkalinity in the aeration basin to handle the amount of ammonia. So John kind of touched on this a little bit on one of his slides, but when you convert 1 milligram per liter of ammonia to nitrate, you consume roughly 7.14 milligrams per liter of alkalinity. So alkalinity is the buffer, and once all that alkalinity is consumed, the nitrifying bacteria will not be able to oxidize any remaining ammonia in the aeration basin. So even if you have everything else, temperature and some of the other things we haven't talked about yet, but DO and enough mass, if you do not have the alkalinity, you will not be able to nitrify any remaining ammonia that remains. And in addition, what happens when the alkalinity is all consumed, the pH will drop out. So, some operators, test their pH. And the CAU, we recommend testing for alkalinity. That way you can kind of catch it beforehand, because if you're only testing for pH and you see the pH start to drop, it's almost too late at that point. But if you do regular process control on alkalinity testing, it will let you know when you need to add some alkalinity so your pH stays fairly neutral and that doesn't drop out. So John kind of mentioned that we recommend maintaining at least 100 milligrams per liter of alkalinity at all times. when there's little to no ammonia in the aeration. We want that 100 milligram per liter buffer. Many small plants in Ohio that we go to, we see a lot of shortages of alkalinity. And if you think about this, many of the gas stations, rest areas, schools, and businesses, a lot of places are installing low flow and sometimes even no flow plumbing fixtures. Well, alkalinity enters the treatment plant in the carry water with the waste. So if you reduce the amount of carry water entering into the wastewater treatment plant, but you still have the same amount of ammonia coming in, you're just reducing the amount of available alkalinity so you can get full complete conversion. So a lot of plants have to supplement their alkalinity. But before I get too far ahead of myself here, so how do we test or check for alkalinity in their aeration basin? Well, just kind of on the mantra of the CAU, we use cheap, quick, and easy and effective alkalinity test kit. It's a titration test. The test we use, you collect a small sample from the aeration basin. You take the clear water off of either your settleometer or from your wastewater centrifuge, which we'll talk a little bit about that later. You add that sample to the bottle, which is shown on the screen. Then you add the indicator reagent, which is usually in a powder pill form, or it can be liquid, and it will turn the water this kind of bluish turquoise, sometimes even a greenish color. And then you'll add your sulfuric acid that's provided in the kit and you'll mix after each drop until it turns the liquid a pinkish color. And you count how many drops that takes. Each drop is the equivalent of 20 milligrams per liter of alkalinity. So if you added 10 drops, 10 times 20, 200 alkalinity. So in this picture, it's kind of hard to see, but here's the alkalinity test, and it's pink liquid here, and that was after 1 drop. So there was less than 20 milligrams per liter of alkalinity in the aeration basin. And you can see over here on the meter that the pH was reading 5.37. So what had happened here, the nitrifying bacteria had consumed all of the available alkalinity in the water, so there was no more buffer, and the pH started dropping out. So in order to increase alkalinity, we recommend adding sodium bicarbonate. And this chart is kind of showing why we recommend bicarbonate. So on the x-axis here is the fractional amount of alkalinity, of the form of alkalinity, and on the y-axis is the pH. And if you look at, roughly about between 6.5 to, 9.5, 10, the dominant form of alkalinity is bicarbonate. Hence, our recommendation of adding sodium bicarbonate when you need to increase your alkalinity. So here's a picture of a 50-pound bag of sodium bicarbonate that you can purchase at most feed stores. I believe this is being added to the diet of cows and horses and everything for stomach issues. So what you want to do is to add this to the aeration basin if you are short on alkalinity, and you always want to try and dissolve this in water prior to adding it. It's not very soluble, so we recommend mixing up a third or half the bag at a time in a large bucket of water, and then dumping that into the aeration basin while the air is running, so it's being fully mixed. If you add the dry powder directly to the aeration basin, since it's not very soluble, it has a tendency to just kind of sink to the bottom, and you may not be getting the full effect of having all that bicarb into the system. The nice thing about sodium bicarbonate is that, well, one, it's fairly cheap, usually $15 to $20 per 50-pound bag at a feed store. It's safe to use. It doesn't pose any corrosion risk to anything at the wastewater plant. It doesn't pose a risk to the health of the bacteria that we're adding to the aeration, that we're adding this to the aeration basin, as well as the health of the operator that's going to be mixing this up and putting it in the aeration basin. So real quick before I get to that, I just wanted to just reiterate one more time. So the goal that you're aiming for is when you have less than 1 milligram per liter of ammonia in the aeration basin, you want at least 100 milligrams per liter of alkalinity in the aeration basin. So that's kind of what the goal that you're always looking for. So when you're doing your process control and checking your alkalinity, and if you're running your ammonia, you want to make sure at all times you have at least 100 milligrams per liter residual alkalinity in the aeration basin. And then now we can jump to our sixth poll question. So polling question number 6 reads, what do you do for process control? A, you use your senses. B, you calculate your mixed liquor suspended solids, your food to microorganism ratio, CBOD. C, you use your cetylometer, ammonia testing, your wastewater centrifuge, core sampler, and DO readings. D, I only do permit testing. Or E, none of the above. Please select an answer.
Okay, I have launched the poll, so go ahead as that comes up and make your selection. I see most people have voted. If you have not, please go in and make your selection before I close the poll. Okay, and I'm closing the poll and sharing the results.
Great, thanks, Helen. So good, about half, a little over half selected what the CAU use for process control. All those tools, some that we've talked about and some that are yet to be talked about in the presentation. Some are doing regular mixed liquor suspended solids test, which the CAU, we don't do that in the field. We want results quick, so we use pretty much all the tools listed in C, but then we also we'll use our senses as well. And then some people are only doing permit testing, 9%, so no process control at all. Hopefully we can maybe talk in that 9% to adding a few of these process control tests into the regular routine, and then 25 are none, which probably not applicable to them. Okay, so back into our flow chart here. So our current slide, we're on box 7, and to get to box 7, we basically ruled out that we have a good enough water temperature. So our water temperature is above 10 degrees Celsius, and we don't have a shortage of alkalinity. So we have greater than 100 milligrams per liter of alkalinity in the aeration basin. So then box 7 brings us to, do we have enough dissolved oxygen in the aeration basin? Is your aeration effluent DO less than 2 milligrams per liter? I think is the question in box number 7. So one thing about dissolved oxygen, it's less soluble in warm water than in cold water. So in the summer, when the water temperature in the aeration basin warms up, you may not have enough DO where maybe you used to have enough DO in the winter and that wasn't a limiting condition. Or maybe you have a timer on your blowers, which I said we advocate for, but maybe there's not enough on time, so we're not adding enough dissolved oxygen to that warmer water in the summer. So in order to check your DO, you take a DO probe. If you do not have a DO probe / meter, Ohio EPA district office, each district office, so the 5 offices across the state, have roughly 8 DO probes as well as wastewater centrifuge that can be loaned out to facilities that they can borrow for, X amount of days or weeks or months. One thing, so you want to take your DO at random times throughout the day, because depending on the load or your flow coming into the plant and timer settings, the DO will fluctuate greatly throughout the day. If you're always taking the DO first thing in the morning before much of any flow arrives, you may have very high DO. But as more flow starts to come into the plant, the morning flush comes in, your DO can sag and drop much lower. And in an upcoming slide or two, we have an example of a plant that was occurring at. So that second bullet point there, photo versus a video, is kind of just what I was a little talking about there. So if you're taking just a one-time reading of a DO, it's just like a one-time snapshot, as opposed to either taking multiple readings over the course of the day, or better yet, data logging, having, a DO probe data log like every half hour or every 10 minutes, what's going on. And then that gives kind of the full picture of what's happening at the plant, as opposed to just a one-time look and say, yep, I've got enough DO. Well, maybe you do at 6 in the morning, but at 10 in the morning, maybe your DO is well below 2 or well below 1. If you have multiple treatment trains in parallel, it's good to check the DO in both trains to see if we have kind of a balance of oxygen in both treatment trains. If one train is getting a lot more flow than the other train, the train that's getting the more flow probably has a lower DO, because there's a higher DO demand there because more raw water, more waste is coming in. On the flip side, if you have several aeration tanks in series, it's good to not just check the DO in tank 1, but maybe tank 2 and tank 3 and so on, how many ever tanks you have in series. Where the raw enters, you're probably going to have the least amount of DO. And then as the flow progresses through tank 2 and tank 3, there should be a little higher DO in each tank, because as that waste is being consumed by the bacteria and converting new bacteria, the DO demand is decreasing as there's less food in the following tanks. So here's this example that I just mentioned. This is a larger oxidation ditch plant. You can see there's 2 oxidation ditches. The one on the left is not in operation, not in service. The one on the right is. This plant only really needed to run half of their system just based on their flows and from past plant performance. But the operator had called the CAU several years ago, many years ago, that saying he was having he was having high ammonia issues. And he said just some of the troubleshooting we do over the phone, we asked, some follow-up questions, have him collect some process control data. And he claimed, I have plenty of DO, it's not a DO issue. So our staff went out to the plant, stuck a DO probe, as well as some other instruments into the oxidation ditch, and we data logged for a couple days just to see what was going on in the wastewater plant. And then when we returned, download the data, here's just a 2-day snapshot of what was going on at the plant. So this red line is kind of that 2 milligrams per liter DO that we're kind of aiming for to make sure that there's enough dissolved oxygen in the plant. And you can see that the time and the day is written down here on the bottom. Overnight, the DO rises, very little demand, a lot less flow in the middle of the night. The first day it reached up to a little over 4 milligrams per liter, and then the morning flush came in, and by noon it was down to just below 1. Stayed below 1 until about 9-10 o'clock at night. Then it started to recover, overnight on day 2. In the morning on the second day, morning load starts coming in, DO demand increases, so the DO starts dropping. And on this day, you can see from about noon to, I don't know, 7, 8 o'clock at night, the DO stayed well below 0.5 milligrams per liter. Well, what was happening is the operator would come in every morning, had his routine, would get there at 6 in the morning and start up the coffee. By 7, he'd go out, take his DO probe out, check his DO, 4 milligrams per liter. Great, no problem. This day, 2.75 milligrams per liter, no problem. Looks like he has plenty of DO. But what was happening is he was only getting that little snapshot, that photo of that time of what was going on. So what the DO logging does is it gives you the full picture, and it sees, there's good chunks of the day where he is well below that 2, and especially on the second day where he was well below 0.5 in that oxidation ditch for many hours. And this was determined to be the cause of his elevated ammonia on the back end of his plant. It's a pretty easy fix for him. He had, we back up again, there was another set of rotors right here. You can see that's not in operation. This is the rotor that is in operation. You can see the mixed liquor really moving right there and kind of turbid. So what he would do is during the day, he'd get there in the morning, he'd turn on the second rotor to allow for increased dissolved oxygen during the day, and then at night he'd go back to just one rotor. So that was one example of needing to increase the air supply to his oxidation ditch, or in a smaller plant in an aeration basin. Here's some other things that may be causing the low DO. Could be maybe you have diffusers that are plugged or clogged, or they're not allowing all that dissolved oxygen to go into the water. Another option is timer settings. Maybe the timer settings need to be adjusted for longer run times to provide more DO into the aeration basin. Another option maybe is you need to turn on another blower during high organic loads, just kind of like that operator did with his rotor. During the day, he turned on the second rotor to input more dissolved oxygen into his mixed liquor. Could be a mechanical issue. Do you have a blower or a diffuser that's, a blower that's not working? I was at a plant just a couple weeks ago where they weren't getting much air into their aeration basin. They contacted me, and we ended up determining they had 2 blowers, and one of the check valves had gone bad. So when one blower was working, most of the air was flowing back into the blower on standby, and it was running it in reverse. So they were losing a lot of air to the atmosphere there, and it wasn't going into the mixed liquor. Or it possibly could be an air leak. Maybe you just have a line that's either above ground or below ground, that's the air's not making it to the aeration basin. Here's a picture that we talked a little bit about of a plug diffuser or block diffuser. This plant was having ammonia issues. Pulled the diffusers, the drop pipes, cut into one, and you can see, look at all of that sediment, silt, solids that have built up over time. Not enough oxygen was going into the water, so they were having ammonia issues. Replaced the diffusers, and within a day, the ammonia was back down to below 1. Here's a picture of that timer again, and as we talked a little bit earlier in the presentation, maybe the timer settings from the winter aren't providing enough dissolved oxygen during the warmer months when the DO is not as soluble. And so maybe you're only getting partial nitrification. Making adjustments to the timer may be as simple as adding on a couple additional runtime periods to make them longer to increase the DO. Instead of having maybe short on cycles, maybe you need some longer on cycles. So that's something to keep in mind and to look into. Okay, so right now we're down to box 9. So in order to get to box 9, we've determined that our aeration effluent water temperature is greater than 10 degrees Celsius, so we have plenty of temperature, that our total alkalinity is greater than 100 milligrams per liter, so it's not an alkalinity issue, and we've determined that we have enough dissolved oxygen, so we've got plenty of DO in the system. That takes us to box number 9, is we're evaluating to determine if we have enough mass in the system to oxidize all the ammonia. So the centrifuge picture has been shown on a couple screens, I believe, so far, and we use this centrifuge to spin down the contents of the aeration basin. It can be used for other parts where we use it for, maybe a clarifier core sample, a return, to return sludge to see how thick they are. And, Andy's going to touch on that stuff a little bit more when it comes to clarifier issues. And within 15 minutes of spinning, we know how many solids are in the aeration tank. If there aren't enough bacteria in the aeration tank, this can be the result of high ammonias. Perhaps you wasted too much out of the system. Maybe wasted too many solids into the sludge holding tank or into your digester. Maybe a lot of the mass is still in the clarifier. Maybe you have a very high sludge blanket. So, the solids are sitting over there, which aren't doing you any good in terms of ammonia removal. So the wastewater centrifuge that we use does the spin in 15 minutes. And we usually typically aim for a spin somewhere between 2 to 4% on the tube. Every plant, though, is going to run better at different volumes. And oftentimes, I see a lot of plants that are running a 1.5 spin that are working just great. Some plants will even work better at maybe a heavier 3.5 or a 4 spin, more material. The important concept here is just making sure that you have enough mass in the aeration basin to oxidize all the ammonia to nitrate. So, I don't want to focus too much on that. You need to have a spin of exactly 2. We just want to make sure there's enough mass there. So if you spin your aeration basin and it comes back at a 0.5 spin, then most likely that's the reason why you're not fully nitrifying. There's just not enough mass in the system. So here's 2 pictures of the centrifuge tubes. The first one is what you fill up to the 100% mark, and then the second one is what it looks like after it's spun down. The nice thing about also the wastewater centrifuge is not only does it give us how many solids are in the system, depending on what you're spinning, but it gives us all this clear water then that we can run our chemistry on. So we can check our alkalinity with this water. We can check our ammonia. We could check our nitrates or orthophosphates, any nutrient monitoring we want to do. All of our chemistry can be run off of that clear water in the tube. So if we determine that we don't have enough mass, let's say we're 0.5 spin, this picture doesn't really fit this slide right here since we're a little over 3 there, but say our spin comes back at 0.5, then we need to eliminate wasting. We want to stop all wasting at that point to make sure we're not sending any more mass out of the system. You may need to bring in mass then at that point, either from another wastewater plant, or if you have a sludge holding tank or an aerobic digester that's being aerated, it's good to usually check the ammonia and alkalinity in that before you bring that back into the plant to make sure we're not bringing in a lot of ammonia. But that option is out there, that if you need to bring more mass into the system, if you have it on site, great. If it's good material you can use with low ammonia, great, bring it back into the system. If not, at a small plant, usually it's just as easy to go ahead and contact the hauler. He's going to charge you X amount of money to go to another activated sludge plant, grab, X amount of gallons of mixed liquor to bring it in to reseed your plant. One thing that you usually see too during cold weather is that a lot of plants will need a little more mass in the system, because as we mentioned, when that water temperature starts to drop, the bacteria aren't as active in the colder environments. And then if you have a real high organic load coming into the system, you just may need more mass just so you have enough bacteria to handle that large amount of organic load that's coming in. Okay, so box 11. When we get to box 11, if anyone's following on the chart, we've ruled out we have enough temperature, we have enough alkalinity, we have enough dissolved oxygen, and we have enough mass in the system. And box 11 is asking us, is looking at, maybe we just don't have enough tank capacity to handle all of the organic load coming in. Now, my little disclaimer here is very rarely does the CAU use this because it requires data that we don't collect and we can't collect in the field and with the tools that we have with us. But if you rule out all the other things that we talked about, so temperature, alkalinity, DO, and mass, then this is kind of the next step to look at to make sure that you have enough plant to handle, you have enough volume capacity to handle the organic load. So to look at the organic loading to the plant, which is calculated in pounds per day per 1,000 cubic feet, 10 state standard states that a plant should not have a loading over 15 pounds per day per 1,000 cubic feet. And the next slide we're going to go through just a sample calculation, but to calculate the pounds, you take the CBOD times flow, which is in million gallons per day, and the 8.34 conversion factor, and that will give you how many pounds per day. And to calculate the cubic feet of the aeration volume, you would take the length, width, and the water depth of the aeration basin, and then if you have multiple basins, you would times it by how many basins you have, and then divide that by 1,000 cubic feet. So let's go through just a quick little example here. So in this example, we're going to say we have 4 aeration tanks or aeration basins in series. They are 6 foot by 16 foot wide by 10 foot operating water depth. If you times all that together, that gives us 3,840 cubic feet. Some of the other information then we need for this formula is we need to look at the flow. So in this example, our design flow is 28,700 gallons per day, or 0.0287 million gallons per day. And then this is the number that we can't calculate in the field. This would actually be an influent CBOD test. So you'd have to do, do a sample on your influent flow coming in, and in this example we just threw in a 238 milligrams per liter of CBOD coming into the plant. So to calculate the pounds, we take that formula from the previous slide, so the 8.34 conversion factor times our flow in million gallons per day times our concentration of influent CBOD, and that gives us 56.9 pounds per day of CBOD. We then calculate how many 1,000 cubic feet we have. So we would take this number that we got from above, that 3,840, divide it by 1,000 cubic feet, and that gives us 3.84 thousand cubic feet. We take the pounds per day of CBOD divided by that 3.84, and that gives us 14.8 pounds per day per 1,000 cubic feet. And if you remember from the previous slide, 10 state standard says that it should be below 15 pounds per day per 1,000 cubic feet. So in this example, it is just below, it is right at, almost at that maximum amount of organic loading coming into the plant in this example that we just went through. So let's say for purpose of moving forward on our flow chart here, that we determine that the plant is beyond design capacity. So say that number came back at 15.8 pounds per day of CBOD. Well, we need to increase the capacity or somehow decrease the flow coming to the plant. So increased capacity is, most likely maybe upgrading the plant. Decreasing the flow could be something to the effect of looking at your flow equalization. If you have flow equalization, maybe looking at in your collection system at times where lift stations are kicking on at the same time that are sending a lot of flow all coming to the plant at the same time. This picture of this chart recorder, this was kind of interesting. This is showing, this is about 5 days here where the flow is off the chart. Well, what was happening here, was that there was a manhole that was found out that was right along a river. And when the river was in flood stage, or when the river level would rise, the river was actually draining into the manhole. So they were taking on a lot of river water that was causing this large amount of flow coming to the plant. Back to kind of our equalization tank, splitter box on a smaller system. This picture is also very interesting. You can see this little cutout, and this is the forward flow. So the flow is being pumped from the equalization tank into this middle compartment. Some of the flow should be going forward into the aeration basin, and there should be a very large cutout on this back plate here where most of the flow would then go back into the equalization tank. Well, in this situation, when those EQ pumps run, all the flow is going to go into the aeration tank. So it's overloading the aeration basin. So it's not even really functioning as a flow equalization tank at that point. So I think that's an interesting picture I wanted to include in here. John had another picture of a cinder block in a flow channel. This was just another way to try to equal out flows between the two treatment trains. Because not only can unequal flow splitting cause organic loading issues, but it can also cause DO issues, as we talked a little bit ago earlier. For example, let's just say one treatment train's receiving 60% of the flow, and then the other treatment train's getting 40% of the flow. Well, the treatment train, the aeration basin that's getting the 60% of the flow, most likely will also probably have lower DO because there's a higher DO demand, since more organic loading is going to that treatment train. Okay, so we're getting close to the very bottom of our troubleshooting chart here. So box 13 is when we've ruled out that we have enough temperature, we have more than 100 milligrams per liter of alkalinity, we have plenty of dissolved oxygen, we have at least 2% spin in we have enough mass, and then we've ruled out that we do not have an organic loading. We're not overloaded due to organic loading and design issues. And that takes us to box 13, which asks us maybe if we have a toxicity issue, something that is causing the nitrifiers something that's inhibiting nitrification, or something that might be impacting or possibly, killing or not allowing the nitrifying bacteria to do their job. We hear a lot of times that something toxic came into the plant and it killed my plant. That happens, but not as often as we usually hear it. Usually a lot of times, toxicity issues happen from something that's internal at the wastewater plant itself. And most of the time it's usually related to very high ammonia coming back from a process, usually related to a digester, going back to the head of the plant and kind of overloading the system with too much ammonia. Anaerobic digesters will almost always have high ammonias being discharged. That's just how they operate. You just have to, you don't want to overload when you're decanning or you're taking supernatant from your anaerobic digesters. You just don't want to send back a large volume from your anaerobic digesters. Aerobic digesters should not have a lot of high ammonia unless you leave the air off for long periods of time, days. And then you go to decant. What will happen is when that air is off for several days, the bacteria will all settle in your digester, and the bacteria will, they're still wanting to breathe. They still want that dissolved oxygen. And once all that oxygen's used up, bacteria will start to die, and then they'll start releasing ammonia back into the water column. So when you decant that clear water from your digester, you could be sending back, 100, 300, 400 milligrams per liter of ammonia back to the head of the plant. In this picture, what we have here is one of those sludge bio bags or eco tube bags that you see a lot of plants have gone to, they waste their sludge into. And what happened here, the operator had left the digester off for many days, and that decant water had a lot of ammonia. It went into the bag, drained out, went back to the head of the plant, and caused ammonia issues at his plant. Other sources of toxicity that can be affecting your plant can be from very long force mains that don't get a lot of flow. The water in those force mains can turn septic. So by the time it enters your plant, you might have really high ammonias. Another possible thing to look at is if you receive septage, mainly just at the very larger systems, you don't ever really know what's coming in on septage. It's stuff that's been sitting in the septic tank for, who knows how many years. So there's going to be a very high ammonia content in that. So here's a picture of a lift station. This lift station had a lot of corrosion. I think it was from a small diameter gravity system. So all the homes of the small village had a septic tank on their property, and the flow then from the septic tank all went to this lift station through like a small diameter pipe. So it's not like kind of your conventional manhole. Everything from the house goes into the collection system. All the solids were kind of held back in the septic tank. And, the community was served by a lot of wells, which had a lot of sulfur in it. So when you put the high organic load into the septic tank, as well as all that sulfur, you're going to get some hydrogen sulfide generated. And then the hydrogen sulfide in the collection system can create a sulfuric acid. So it had corroded pretty much everything that was in this lift station. So that's just one example of in the collection system of a possible toxicity issue. But remember, kind of the takeaway from toxic issues is always look inside the fence first. Always look inside the wastewater treatment plant to see if it's something that you might be doing inadvertently that's creating an upset or a problem in your aeration portion of your plant. And here's a simple toxicity test for ammonia. It's an ammonia uptake test. In this example, landfill leachate was added to this. The community wanted to accept this landfill leachate, and they were afraid that it was going to cause some toxicity issues with their plant. So what was done here, several samples of mixed liquor were collected from the wastewater treatment plant, and then different volumes of landfill leachate were added to each container. They were aerated with a small diffuser, and then the alkalinity and ammonia was tested every hour to see if one, if the ammonia was being reduced, and two, if the alkalinity was being consumed, showing that treatment was occurring. And then here's just a chart showing the x-axis shows the ammonia concentration, and then the y is just the amount of time. And as you can see, each hour when a sample was taken, you can see both the ammonia and the alkalinity were being reduced, were being lowered. So that just showed that the bacteria, the nitrifying bacteria, were not being negatively affected by the landfill leachate, the ammonia in the landfill. It was still able to nitrify. So we got another poll here. This is poll question number 7. So which reads, you can call DEFA CAU for assistance during which months of the year? A, June through August only, B, March through May only, or C, anytime during the year. Please select an answer.
Okay, I have launched the poll. So when it comes up on your screen, please click the button and then hit submit once you've made your selection. And it looks like a lot of people have already voted. If you have not, again, please click on the button to make your selection and then click submit. And I will close the poll shortly. And I'm sharing the results. There you go, Nick.
Okay, thanks, Helen. And yes, we are available anytime during the year. We do not just work in the summer or in the spring. We are available any time of the year. So our contact information will be in at the end of the presentation. And as John mentioned earlier, you can contact us directly anytime, or if you happen to not have our contact information in the future or you misplace it, you can always contact your inspector and ask to, for a contact for the CAU. So what we're going to do now is we're going to give everybody a 5-minute break. Let you stretch your legs and go to the restroom, and we will return in 5 minutes.
Okay, in case you are within earshot, we will resume the webinar in 2 minutes. So you have a couple minutes to go on your break. Okay, heads up, our break will end in 1 minute, so please be ready to go in 1 minute.
Okay, Helen, it's time to resume the webinar.
Okay, thank you, Mike. And before we start up again, just a couple quick reminders. Again, there are handouts in your GoToWebinar platform. If you look on the document icon, you may want to download those when you have a few minutes. There's a PDF of the PowerPoint, there's the manual, and then there's the CEU fact sheet, and then also a flow chart. And again, a reminder on the polls, it's best if you have your screen full-sized. To get there, there's a little icon on your GoToWebinar interface. It looks like a square with 4 arrows. So hit that. And then if you are having issues with the polls, please send us in through the Q&A pane that you are having issues with the polls. You can answer it there. The report that we pull at the end of the webinar, we will see you were having internet issues. So we'll be able to tell that from there. Okay, you can go ahead.
All right, good morning, everybody. This is Andy Gall, and I'm out of the Northwest District Office. I am going to take over the presentation here and talk about the right side of our activated sludge process control chart. This is the side of the chart that deals with settling issues. So you've done a good job in your aeration tank. You've converted your ammonia, and that's the first step to good treatment in your wastewater treatment system. And now we're moving on to the separation portion of the treatment process, which occurs in the clarifier, and you need to have good settling in order to maintain compliance so that the water that you discharge from the plant will meet NPDES permit limits. So back to our chart here. We're going to start here at the top, and we're going to have our ammonia is less than 1. But we're having some settling issues. So we're going to concentrate on the right side of the chart here. And the first part, or the first part of the chart, excuse me, is going to be settling issues, and then the right side of the chart is going to be clarifier issues that we have. So we'll start here on the first part. So you've got complete conversion, and now we need to use our settleometer tools to do a separation analysis. We'll use our settleometer, which is the perfect clarifier, basically meaning that there is no hydraulic inputs or outputs that influences the clarifier or the settleometer, and it allows us to look at the settling closely to see how the biomass actually settles in our wastewater treatment plant. And what we're looking for is we want to get our settling below 800 in the first 5 minutes. There can be causes of poor settling. So you could have too much mass in the system. Or you could be growing a biology or a biomass that is not dense enough to settle and is too buoyant and won't settle. So you'll have to make some adjustments in order to address that. You want to use, so what we're looking for, like I said, in the first 5 minutes is we want settling to go under 800. If it's above 800 in 5 minutes of watching your settleometer, then we have a separation issue and we need to investigate it. So again, we're looking for this picture of the settleometer, the sludge in the biomass to settle so that it is under 800 in the first 5 minutes. And what we found is that when that occurs, you have a low loss of solids out of the clarifier during varying conditions that the wastewater treatment plant sees. Now moving on down the chart, if your settleometer is above 800 in the first 5 minutes and it does not settle below that, then maybe there is a problem with how things are settling. And the next tool that we use to investigate that is our process control centrifuge. So what we do is we take a sample of your aeration tank effluent and we put it in our centrifuge and we spin it down in 15 minutes and we read what the centrifuge spin is. And what we find is if the centrifuge spin is greater than 4%, we may have too much mass in the system and we would need to waste in order to address that mass system and hopefully improve our settling. At the same time, if we have less than 4%, but we still have poor settling, we will do what is considered or what we call the diluted settleometer test. So we take two different settleometers. In the top picture here on the right is a settleometer that's got 100% aeration tank effluent. And then the one on the left has 50% aeration tank effluent and then 50% clarifier effluent. And we watch that for 2 minutes to see if we have good settling and how the settling differs in those two. During the first 2 minutes, if the one on the left that is diluted with the 50-50 settles better than the one on the right, then we know that we have too much mass in the system and we need to waste. If we waste theoretically half of the mass out of the system, we should get settling that mirrors this settleometer here on the left. Now jumping down here to the picture at the bottom is the same diluted settleometer test with a different biology. Again, 100% aeration tank effluent on the right and a 50-50 mix of aeration tank effluent and clarifier effluent on the left. And as you can see, there is really no discernible difference in these two settleometers. What we have occurring here is we have a lightweight mass that doesn't settle. So it's not that we have too much mass in the system, it's that the mass that we're growing does not want to settle. That in a settleometer that looks like this during the 2-minute test may be an indication that we have a filament issue that we'll need to investigate. So this here is our a video of our diluted settleometer test. And so as you can see, we've got our samples in and we're stirring them up. And you can see that, it's gently stirring and the paddles are now removed. And as we watch it here, you can see some of the clear water starting to come up from the bottom of each settleometer. The settleometer on the left is full strength, and the settleometer on the right is our diluted settleometer. Now, as you can see here, we're 30 seconds in, and we're starting to get some settling here. We're getting clear water on the top, but you can see that the flock is starting to form. You can see these bubbles. That's the clear water making its way up to the top, and the settling is coming down. So it looks like in this particular settleometer, we're gonna achieve our 800 settling, or less than 800 settling in the first 5 minutes. And this is an example of a concentration example. As you can see, the one on the left, it's the full strength. We're 1 minute and 30 seconds into this, and we don't really have very good settling. Very little clear water on the top. And what we're seeing is when we look here at the one on the right, the diluted settleometer settles much better. So what this settleometer test is telling us is that we have too much mass in the system, and that we need to waste some mass out of the system into our sludge holding tank, or have someone come and pump out some solids from the aeration tank and clarifier in order to improve our settling here in this example. Now, moving on, here's another 2-minute diluted settleometer test. And this one is an example of density. Again, we have 100% aeration tank effluent in the settleometer on the left, and a 50-50 mix of aeration tank effluent and clarifier effluent on the right. Now, as you can see, we really don't have much going on in either one of these. We don't have flocks forming. We don't really have much settling occurring. It just kind of, there really is no change to it. We can watch this all day and probably not get much change. What this is starting to tell us is that we probably have a filament issue. It's a low density biomass that we've grown, and the filaments keep it from forming flocks like we saw in the previous example. And by not having flocks, we don't have a good settling. So as we start to go through this, when a plant that has a low density biomass with filaments, high flows will push solids out of our system in this type of a system. We'll get solids lost out of the clarifier, and that'll go out onto your sand filters, and that'll become your nightmare per se. And we'll get more into that in the oncoming slides here. So here we are at the end of the 2 minutes, and it looks very much like it did at the beginning of the 2 minutes. Again, no change in this settleometer, an indicator of filaments. So people always ask us, what's our wasting rate number? And the answer is that it's really dependent on your plant. You need to use the compliance tools to do some process control to figure out what your operating window is for your plant. If you don't have enough biomass on the left, you're not going to get complete conversion and low ammonia. And then if you have way too much biomass, you're going to get poor settling. So you want to use the compliance assistance tools and process control to make sure that you figure out what the compliance window is so that you have complete conversion of ammonia and that you have enough biomass to have good settling and not too much biomass that you have poor settling. So moving on here to box 17. And this is an example of where we have filaments that are impacting our settling. So we're looking at this settleometer picture here. We've got greater than 80% settling in the first 5 minutes, an aeration tank spin of less than 4%, and a diluted settleometer analysis that shows very little settling that is occurring during that. And then we also get some coning in our settleometer. So that can be a cause of filaments. Now, one area that is also an indicator of filaments is excessive brown foam on the aeration tank or the clarifier. Biological foam occurs in a low F to M environment in your wastewater treatment plant, which basically means that there's more mass in your wastewater treatment plant than food coming in. And that creates an environment for filaments to grow. And we call that a low F to M filament. So that is an indicator of filament growth that we look for as a visual cue. And so the solution when you have a low F to M filament that you're growing in the wastewater treatment plant is to change your operating condition. And in order to do that in the low F to M environment, we need to waste from our system and get some of the biomass out so that the influent food source matches the amount of mass in our system. So we increase the wasting rate from the plant to reduce the biomass, and we use our centrifuge process control tools to check how much mass that we have in the system. So typically, for example, your process control centrifuge may show a 8% spin, and you want to reduce that. And remember, as we said, our target is a 2 to 4% spin. So you want to, reduce the mass out of the system in order to get things back into balance, and check with your centrifuge as you waste to see how many solids you have in the system. Your settling should start to improve because you've started to waste filaments out of the system. Then at that point, after you've wasted the filaments out of the system, you can start to remove this foam from the top of the clarifier. That will then improve things in your plant and help to reduce the impact of that low F to M filament. All right, it's time for another poll question. And the poll question is, what kind of issues can DEFA's Compliance Assistance Unit help with? A, operational issues. B, design issues. C, administrative issues. D, all of the above. Or E, not sure.
And I have launched the poll, so go ahead and make your selection. And it looks like most people have voted. If you have not, go ahead and please make your final selection before I close the poll and share the results. Okay, and I am sharing the results, Andy.
All right, thank you, Helen. All right, looks like everybody's still with us and paying attention. And if you selected all of the above, that is the correct answer. We can definitely help you with operational issues. We can also help identify design limiting issues. Can also help advocate for the wastewater treatment plant when there's administrative issues and things that you may need to help you operate the system as an operator or things like that. So moving right ahead here, jumping down through our chart. So there are three types of filaments that we look for. The first one that we talked about before the poll was our low F to M filament. The next filament that we look for is a low DO filament. And one of the more common causes of filaments is a low DO concentration in your aeration tank. So typically when we have a low DO in our aeration tank, we're not going to have the brown foam that we have with a low F to M filament. But we could use the ammonia test and see that we have an ammonia value much higher than 1 at the same time that we have low DO. And basically what we're looking for is long, low levels of DO, less than 1 milligram per liter, or really short, deep levels of low DO. And so the longer the DOs in your aeration tank are low, then it is more likely that you have conditions that will grow a low DO filament. And to do that, we use our data logging DO meter. This is an older model, but it allows us to deploy the DO meter and start to see how the DO fluctuates in the plant during the day. Now, this graph here is showing the data from a DO meter that we deployed in a plant. And you can see on the left is the DO readings starting at 0 and then going all the way up to 6, and then the time period across the bottom. And as you can see in this particular example, on Saturday night, overnight, we had plenty of DO. I believe this was at a campground. The DO got up to 6 or just below 6, high 5s, and then as people woke up on a Saturday and flow started coming into the plant, the DO started to drop around 8 a.m. And somewhere between 8 and noon, the DO dropped and was low, less than 1 all day Saturday until well into the night on Saturday night. Looks like it started to recover briefly late Saturday night, early Sunday morning. And again, it recovered. And then again on Sunday, it dropped back down. So there was periods of low DO, which is right as an environment that will be ideal for a low DO filament to grow. And then you can see on Monday, we got back into a more typical pattern where you can see the load coming into the plant and the DO increasing and decreasing with the load throughout the day. So by deploying the DO meter and doing some data logging, you can see the various points that the DO changes and figure out what adjustments you need to make. And so I guess, moving back, if you have low DO, you basically need to increase the DO in your aeration tank in order to get rid of those low sags and get that DO level up to change the environment to eliminate those conditions for low DO filament growth. The third type of filament that we look at that can cause a settling issue in your plant is septicity filaments. And so you have a settleometer where you have pore settling. It's still above 800 in 5 minutes, but you have a lower aeration tank spin. Your settling, again, is not caused by too much mass in the system, but more filaments. And so if you don't have a low DO issue that you've identified by doing some logging or monitoring with the DO meter, you may want to investigate for septic sources. Septicity can cause filaments to grow as well. If you see things if you have to use things like odor ban, or you have a strong rotten egg odor, that can be an indication of septicity. Do you have rusty grating on your plant? Lots of corrosion can indicate septicity. Are the grates on the aeration tank look like this picture? Definitely not something you want to step on. Is the lift station got a lot of corrosion and things like that? In those instances, maybe you have septicity coming in from the collection system. Long force mains with low flows can be sources of septicity as solids start to break down before they get to the plant. Do you have internal sources of septicity? Do you have an aerobic digester that's got a lot of solids in it? For example, it costs money to haul the sludge out of the plant, so a lot of operators like to thicken and decant as much as possible. Periods where the air is off in an aerobic digester for long periods of time is a good environment for septicity filaments specifically to start to grow. Do you have a long detention time in your clarifier? Do you have solids breaking down on the bottom of the clarifier before they're returned to the aeration tank? These can all be sources of septicity that you want to investigate and address in order to change the conditions that are ideal for septicity filaments to grow in your plant. Okay, so we made our way down the left side of the settling chart, which is a filament portion of the chart. And now we're going to move on to the right side and look at some clarifier issues. But before we do that, let's take another one of our famous poll questions so that you can get your operator contact hours. And poll question number 9 is, does each Ohio EPA district office have a small library of process control tools that can be loaned out? A, yes, B, no, or C, not sure.
Okay, I have launched the poll, so go ahead and make your selection. Looks like a lot of people have voted. If you have not, again, please make your final selection. I will be closing the poll shortly. Okay, and I'm sharing the results. There you go, Andy.
All righty, thank you, Helen. And that those of you that answered yes are correct. Each Ohio EPA district office has a library of process control tools that can be loaned out to operators and plant owners to do these process control tests that we're talking about here today. Specifically, the more expensive items, the process control centrifuge. Each district office has several of those, as well as DO meters. We also have settleometers and core samplers that we can loan out, as well as alkalinity test kits. So if that's something that interests you, we are more than happy to bring those tools out to you and leave them at your plant so that you can use them for a period of time to do process control testing at your plant. Okay, so jumping back into it here, you've done your settleometer test. You don't have, you've got settling that's less than 800 in 5 minutes, but you're still having solid loss from your clarifier. So we need to start investigating that. The number one indicator of that is solids loss in the stream. Obviously, we don't want that. It's the we want to make sure that we aren't having solid loss in the stream. Some of the things that we start to look at that may identify a clarifier issue is biomass buildup in the effluent weir. Too much solids in our clarifier can also be an indicator of a clarifier design issue or an issue that we need to look at. The other thing that you need to take, or that we take into account, is sand filters. Do we see solids build up on the sand filters? Now, in this picture, this is a young sand filter. We don't have a lot of solids loss. Water's being dosed onto the sand filter and is going down through the sand in a relatively short period of time before it reaches the walls of the sand filter. Now, here's an example of a sand filter that is, I guess we call it middle-aged. We aren't fully ponded, but as the filter is dosed, the water is not going through the sand as quickly, indicating some solids buildup from solids loss from the clarifier, and it reaches the edge of the walls of the sand filter before it drains through all the sand. So we're getting decreased performance out of our sand filter. And this here is what we would call a deceased sand filter. We've got on the left, definitely a ponded sand filter. A lot of solids, water's not going through very quickly. And then here on the right, you can see solids build up, covering all the sand filter. And so in this instance, we definitely want to have those sand filters cleaned in order to restore performance. But the sand filters are not really the cause of our problem. It's more the clarifier issue that we should back up and investigate. Typically, we'd recommend that you get 2 to 3 months of service out of a sand filter before you need to change it to a different one if everything is operating correctly. As you lose more solids from the sand filter or from your clarifier, you'll get decreased life out of that filter. Now, if you've got good settling and you've got low ammonia, you're in that compliance window. You've got acceptable separation, you've got good settling, and your settleometer under 805 minutes. You know that you shouldn't have a solids loss issue. If it's above 805 minutes, then you probably need to make some adjustments to the clarifier or investigate for possible filaments. And by measuring and taking a look, you really get an idea of how big your operating window is. If you've got complete conversion and ammonia removal in your aeration tank, good settling, you know where your compliance window is. And so by taking regular process control samples, you can make adjustments as needed. You as the operator have a little bit more control of the plant. Now, if you may still be, in compliance and whatnot, but you have a less smaller operating window, I guess, if you don't have some process control samples, or at least that's what we would advocate. Your process or your window is a lot smaller when you don't have data to support your operational decisions. Moving into box 25 though, if we still are having solids loss, one thing that we want to look at is the settling in our clarifier. As the sludge starts to settle in our clarifier, it comes in from the aeration tank, if you see my cursor, and it goes into the clarifier and it starts to settle into the hoppers, and you start to build up this sludge blanket. As your sludge blanket increases, your clarifier capacity starts to go down. So you need to return sludge from the bottom of the clarifier back into your aeration tank in order to maintain that proper blanket depth. You do that through adjustment of your return activated sludge rate that controls the amount of sludge pumped out of the bottom of the clarifier. You want to keep your sludge blanket about 20 to 30% of the depth of your clarifier, and you can use a core sampler to verify that. Now, here's a short video or a video of a clarifier system that is operating well. And as you can see, the biomass is coming in here at the top. That's simulating it's coming in from the aeration tank. And then the plate kind of disperses it. And then the sludge settles into the hoppers of this clarifier. You can see that, the hopper 1 is filling up and then spilling over into hopper number 2, and the blanket is within 20 to 30%. The sludge is being returned here, if you can kind of see the white pipe here in the back, with a geyser style pump, which is using air and pulsing to return the sludge to the aeration tank. So as you can see in this example, we have good settling sludge and a clarifier that is operating quite well. Now let's move on here to a clarifier that isn't operating quite as well. We got a high blanket depth in our clarifier. As you can see with my cursor, almost 80% of the clarifier has got, a sludge blanket. So in this instance, we have to investigate what is causing that issue. Is our return rate too low or too high? Is it in the right area? Do we have too much mass in the system and just need to waste? When we have this situation, as you can see, too high of a blanket, the biomass will enter in from the aeration tank and it will skim across the top of that blanket, and then you'll have solid loss out the effluent weir. Now this is another video, and this is an example of a poor settling sludge or poorly operated clarifier. And in this example, what we have going on, you can see the sludge coming into the plant, or coming in from the aeration tank here at the top and going in to the hoppers and going across the full hopper 1 and hopper 2. And what we have going on is we have the RAS rate is too fast, which is causing the tank to be mixed and reduces our settling characteristics in this clarifier. So what we want to do is we want to make adjustments to the return activated sludge rate, or the RAS rate, to match the settling characteristics of the sludge that we've got grown. This will help take some of that hydraulic pressure off of our clarifier and should help improve our settling. So how do we do that? Now this is a picture of an operator, Rodney. He looks pretty happy, but he probably shouldn't be. Looking at his clarifier core, he's got definitely a lot of sludge in his clarifier. 1, 2, 3, 4, 5, 5.5, 6 feet of sludge in his clarifier. So he's definitely got a high blanket. He probably needs to make some adjustments to his sludge pumping rate to get rid of and address that issue, to reduce that blanket in his clarifier. If he's got too much mass in the system overall, he may need to waste out of the plant. Another cause of clarifier or solid loss from your clarifier could be hydraulic issues. And some causes of that can be poor flow splitting, density currents, which leads to short circuiting in your clarifier, or location or elevation of your effluent weir in your clarifier. If your clarifier weir is not level, you could have solids loss as well, or if it's put in the wrong spot in the clarifier. In this example, we have a flow splitting box that's got no weirs, no control, for directing that flow. This is a live example, or an example of a hydraulic issue that was our team investigated several years ago. As you can see, this is a channel, and it narrows down here at the end in an attempt to control the flow. That's a poor way to do it, because in this example, the way it is currently set up, all of the flow goes to this clarifier here at the very end, and none of the flow goes to this clarifier here at the beginning. So we did some investigation using dye, and we put dye into the system, and it showed us that the clarifier in the back received all the flow because all the dye went to that clarifier, and the clarifier at the front received less flow. So here's the picture with the dye in that back clarifier because all the flow went down to that end. It didn't know to turn right into this first clarifier. So we came up with a custom solution. This is Keith. He created some plywood plates that were installed in the channel there to direct the flow. And what you can see is two of them are about the same size, and then one of them is shorter. And so the shorter one was put in the far channel, and then the two taller ones were put in there, and we were able to redirect the flow using those plywood plates. Again, here's the before the plywood plates were installed. You can see the clarifier 3 got most of the flow. And then after the plates were installed, the flow to each clarifier was better split. It's not perfect, but as you can see, it came closer together. 3 and 4 are a little bit closer than they were, a lot closer in the beginning. So that's how hydraulic issues can impact your clarifier. Density currents can cause another issue, short circuiting and solid loss from your clarifier. Here's an example of installing some baffling and clarifier in order to reduce solid loss from density currents. Basically, they mounted some angle iron to the walls of the clarifier in the middle, and then put boards across the clarifier to help break that up and reduce the solids loss and carry over from the clarifier. You can also do the same thing in a package plant clarifier. The lattice will break up a density current. In this example, we created a flocculation baffle at the influent end of the clarifier by extending the scum baffle down to within 2 feet of the bottom of the clarifier. And that just breaks up that density current that could cause solids to be lost out of the clarifier. Another option in a package plant clarifier is to put a baffle midway through the tanks. This is a more difficult option, but again, one that can be done with some angle iron on the side of the clarifier and then some boards and some baffling lattice through there. One thing to keep in mind is that you want to have the top of that baffle and lattice wall be below the surface so that your skimmer will still function for all of the clarifier, that you can get some of that floating solids back into the skimmer system and things like that. And here's just another picture of that midway through. You can see it's between the two hoppers in the clarifier. And that'll help reduce solid loss across the top of the clarifier. And then the final thing that you can look at for solid loss in your clarifier or potential causes of solid loss in your clarifier is your effluent weirs. Are they located in a proper spot? In this particular example, you had an effluent weir that was within the solids would come across the clarifier, hit this back wall, and then spill over the side. In this instance, we took the weir out of service with some plywood and some C-clamps and stopped that solid loss over this side of the weir. And it's time for another poll question. What can cause solid loss? A, high influent flows. B, too much biological mass. C, too little biological mass. Or D, too slow of a return activated sludge flow rate. Or E, all of the above.
Okay, and I have launched the poll, so please make your selection. Okay, it looks like most have made their selections. So if you have not, go ahead and make your final selection. Okay, I'm going to close the poll and share the results. Here you go, Andy.
All right, thanks, Helen. All right. Thanks everybody for answering that poll question. And it is, you are correct, all of the above can impact our settling in the clarifier. So we can also use our process control tools in order to set our settling rate in the clarifier or our return sludge rate to get optimal settling. And the first thing that we use to do that is our settleometer. We set it up and we watch it for a half hour and we record the results every 5 minutes. And then we graph it out here. Our volume is on the left and our time is on the bottom. And in this particular example, we graph it out and we want to locate the knee of the curve. We want to find where the settling starts to slow down and kind of level out. So in this particular example, we're close to 45% or so where the knee of the curve is. And then we take our aeration tank. So the knee of the curve is really the ideal settling that we want. Then we take a sample from our aeration tank and our return activated sludge, and we spin those down. And then we use those spin numbers to calculate our ideal RAS rate. And so, as you can see here, as we work through, this is our settling, and that's the knee of the curve. And that occurs at about 20 minutes. And so the ideal settling is at 42. And in 30 minutes, we get down to 38. but what we do is we back it up one because we don't know, you know, we don't know exactly where that occurs, so we don't want to waste too much out by backing. So we'll back it up one for our calculation, and our target settling is 50% in 15 minutes. So now we need to match our return sludge rate with the spin. And so we know that we have 100 in our settleometer, and our aeration tank spin came back at a 3.2, and we settled at 51 in 15 minutes. And so we use that to calculate our target RAS rate. Based on those numbers, doing the calculations, 100 times our spin at 3.2 divided by 51 of our settling gives us a target spin rate, or our target return rate, of 6.3%. So we'll need to adjust because our actual RAS rate is 8.8%. Some of the other things that we can look at is the surface overflow rate of your clarifier. Do we have too much velocity going across the surface of the clarifier for the biomass to settle? The other thing that we can look at is the solids loading rate. Do we have too much solids being loaded onto the clarifier that impacts our settling and causes solids to be lost from the clarifier? Here's an example of the surface overflow rate from a clarifier based on, you know, what it is designed. And here's kind of an example of our solid loading rate from a clarifier. Basically, what we're trying to drive home here, though, is to use the quick method, quick, easy methods to adjust your solid settling rate and come up with the best rate for the sludge that is grown, or the biomass in your plant. Use a settleometer and use the centrifuge. We want to have our centrifuge spins for an aeration tank to be somewhere between 2 to 3, and then the return activated sludge to be somewhere between 2 to 3 times the aeration tank spin. If you start to get a return activated sludge spin of 4 times the aeration tank spin, you can get problems and settling, specifically with settling in the clarifier. You can use the core sampler then to confirm if you have too high of a blanket in your clarifier or not. Here's just an example of evaluating the correct return activated sludge rates. And with that, I think I have wrapped up the clarifier section or settling section of our process control chart. I will turn it over. Let's take a quick poll. DEFA CAU can A, perform plant performance evaluations, B, troubleshoot problems, C, create cheap, innovative solutions, D, provide on-site training, or E, all of the above.
Okay, I have launched the poll, so please make your selection. And John, I think you're up next. As far as time, we can extend a few minutes and I can shorten up the wrap up.
Okay,
But,
I will go quickly. How's that? So,
okay, yeah, I would say, you know, till 12:10 we can definitely
okay.
do, and then, like I said, I'll do a super short wrap up.
Okay.
Okay, it looks like most have voted. If you have not, go ahead and please make your final selection. You know, you guys just pack so much information in. It's hard.
That's why we go to plants and do it there. So,
Okay, please wrap up making your final selection. And I'm closing the poll and sharing the results.
well, looks like all of the above got most of the issues, but we do all of those things. So, okay, so I'm going to do a really quick thing on disinfection. Okay, so there are 3 types of disinfection in Ohio. There's chlorine, tablet chlorinator and dechlorinator. It's a chemical process. There's peracetic acid. This is a new technology that some plants are using, and it's also a chemical process. And there's ultraviolet light, which the light waves disrupt the bacterial DNA, and so they can't reproduce, and that's a physical process. Okay? So, look at chlorine first. It's a balance. You have chlorine and dechlor. You have a bacterial limit, and you have a chlorine residual limit. So what you need is enough chlorine to get the kill, and enough kill the bacteria, and enough dechlorination to meet your chlorine residual. Okay, so that's a little bit tricky. Right there is a sodium hypochlorite. That's a liquid, and it's fed into the with that peristaltic pump there on the very left-hand side, fed into the chlorine contact tank. This is a tablet chlorinator that will have hockey pucks of chlorine in it, and well, and the one on the right there has doesn't have the tubes in it, but because this treatment system goes to a impoundment, not to a river, so chlorine will dissipate. And these are the chlorine tablets, which are white, and the dechlor tablets, which are green, so you don't get them confused. And there they are in a tablet chlorinator. Okay? So, in order to make sure you get the kill, you have to check the free chlorine concentration. And this is after the chlorinator in the chlorine contact tank. So, you need grab sample, clean tools and containers, and you must have 0.2 milligrams per liter of free chlorine residual in the tank. Okay? That just means that you have enough left over in order to get the kill, and it's not 0, okay? Because if you have 0, some bacteria will probably survive. So this is my DR900. This is checking free chlorine. That's 0.69, which is pretty high. And the one on the right is 0.14, which is not quite enough, not quite 0.2. Right there is the one that's a little bit better, 0.3. Okay, that's a little bit better. So, okay, so let's go on. But you have to check the total chlorine concentration after the dechlor. Okay, so again, you need a grab sample with clean tools and containers. It must be within the permitted limit. And if the measured value is less than 0.05 milligrams per liter, you are presumed compliant, even if your permit is lower than 0.05. Both of these are less than 0.05, so this would be perfectly fine. Okay. So conversion first. Incomplete conversion will impact disinfection. Okay, so if you have CBOD or ammonia in there, the chlorine will interact with those, and it will not use up all the, or it will not disinfect all the bacteria. Chlorine is more effective in clean water. And if you have no tablets or no hypochlorite or no disinfection, then you won't have any kill. And the tablets must be in the water, not bridged. Also, if you have some solids loss into your chlorine contact tank, like this one, like almost 2 feet of solids, it's going to work on that rather than the bacteria, okay? So you might use your core sampler to check in the chlorine contact tank to see how many solids you have in your chlorine contact tank, okay? Okay, let's look at peracetic acid now. Peracetic acid is gaining a following. It's similar contact time as chlorine. And I called Hach and they said, well, you can test concentration with PAA with chlorine test kit. Well, okay, I did it and it worked, but I would suggest you call them and see if that really does work again. But they said you multiply the meter result by 1.07 to get a PAA concentration. Seems to be an effective disinfectant, but apparently no residual in the receiving stream. But is it economical? Well, I'm not sure about that, so I didn't pay for it. So this is a PAA tote. This is the sample. This is the PAA is 21.5%. It has a little bit of hydrogen peroxide in it too. And there's a peristaltic pump that you will put it into the chlorine contact tank right there, and it works pretty doggone well. So now we'll go to ultraviolet disinfection. Ultraviolet is very effective if the light can penetrate the water. There are some problems though. You have to have a proper hydraulic design. I was at a treatment system that flooded out the UV system, and the stuff that the effluent that came on the top of it didn't get disinfected, and that was a problem. If you have low suspended solids, if you have high suspended solids, that will shade the UV from penetrating the bacteria and scrambling their DNA. And the bulbs must be clean, okay? Because the bulbs will heat up a little bit and you'll get some scaling on them. And of course, the unit must be powered. Here are 2 package plant systems. The one on the left is a UV system, and you can actually see the light. Well, you can't see it right there, but you can see that it's on because you can see the light going through the water down there. But the one on the right, you can't see it. It comes in on the right-hand side and goes down, and then comes back up. And the bulb is in the bottom of that thing in the middle, okay? And it's kind of hard to see if it's working or not. Right there are some solids in the effluent of the UV channel. You can see the solids up there. But it works pretty doggone well if the light can penetrate into the bacteria. This is a larger system where they have quite a few lights, and they have 2 banks of these, and there's 1, 2, 3, 4, about 10 of them there, I think. And you can see that they're working because you can see the light shining out of the bottom. And this is a bigger plant, and these are vertical, and but this is when they are out of season. In Ohio, in the streams, they have to disinfect from May 1st until October 31st. And if you're a Ohio River discharger, you have to disinfect all year round. But this one goes into a river, and so people aren't in the river in the wintertime, so you usually don't have to do it then or disinfect it then. And there is that same treatment plant working, okay? So the light doesn't penetrate the water. Okay, substances that impact UV transmission are things like iron, dissolved iron, ions, nitrate, but it has to be pretty high nitrate, dissolved organic matter will turn the water a little bit brownish, and that can mess up the ultraviolet light a little bit, and a variety of chemicals, which are pretty rare in large quantities. So you probably don't have to worry about those chemicals very much. So how good is your effluent? How do you know? Well, I have a UV transmissions meter. And if you aren't getting good kills in your UV system, call me. I can bring this out and I can run it. What you do is you put a DI water in it. You have a little square cuvette and you fill it with DI water and you calibrate it. And then you put it in, okay, there's calibrated with 100%. And then you pour that out and then put the effluent in. And if it's, the standard is 65%, and this is a little bit lower than that, 48.4%. So that might be a little low to get the kill that you need to meet your permit. But anyway, measure, don't guess, okay? So I think, quick poll. This is the last poll, I think, okay? So, Helen?
Okay, the question is, the assistance provided by DEFA CAU cost how much per visit? Select 1, $50, 2, $100, or C, it's totally free. So please make your selection.
So I'm sorry I went over just a little bit of time. I hope everyone got the disinfection essentials, and this is the last quick poll. So there'll be just a couple more slides after this, and that will be the end of it. So.
Yes, it looks like most people have voted, so if you have not, go ahead and make your final selection. I'll close out the poll here shortly. And we will get you out, maybe 5 or 6 minutes later than we originally planned. Not too bad. Okay, and there are your results, John.
Okay, it's totally free, which it is. So, okay. Although I could use the $100, but it's totally free. So, questions? Okay, but anyway, here. This is where we are located at the EPA, epa.ohio.gov, and you go to divisions and offices, and you go to the environmental and financial assistance. You look for wastewater treatment plants, and it says get free technical assistance to improve compliance. And then go to technical resources, and that's where the activated sludge process control and troubleshooting chart and manual are located, plus a whole lot of other things. Or if that's too much trouble, you can email me or Andy or Nick. Those are our email addresses, and we can send them to you, okay? So that's it. That's the final part of our slide. So I'll turn it over to Mike or Helen or Mike or whoever's coming up next.
Okay, well, thank you. Thank you, John, Nick, and Andy, for your great presentation. And thank you to everybody for attending and hanging on for the last extra few minutes. As I mentioned earlier, the webinar has been recorded, and you'll receive an email after the webinar with a link to the recording and a link to the session survey. The survey will pop up once the webinar ends. And please note, you will receive a certificate of attendance in a separate email from an Ohio EPA staff member. We try to get those out within a week, but you're not going to get an email with the certificate from GoToWebinar. As a reminder, CEUs are available for the session. To receive credit, please respond to the questions about CEUs in the session survey. So go ahead and put your numbers in when you're prompted. We would also like to bring your attention to our Encouraging Environmental Excellence program. It recognizes entities for exceptional achievements in environmental stewardship. There is a program included about communities, so take a look at that slide later in your PowerPoint PDF. And before we end for the day, here's some upcoming training opportunities. On May 17th, we have a construction stormwater general permit webinar. On June 21st, brownfields funding opportunities. July 12th, environmental regulations in your community. And to register for upcoming webinars, you can go to our training event calendar. That's on our main web page. It's also on the bottom of each web page in the footer. There's a link to it. If you miss past webinars, you can go to our YouTube channel, and that actually can be accessed through the link on this slide, or on our web page, there's a link to YouTube at the bottom on the footer. And to receive notifications for upcoming webinars, you can go to our Customer Support Center, create an account, go to the option Subscribe to Updates, select All Trainings, Webinars, and Conferences. And you can go to the link on the slide, or the link to the Customer Support Center is also at the bottom footer of each web page. With that, we'll end today's webinar. Thank you again for joining us, and have a great day.
Thank you, Helen.